Welcome to session 2, right. So if you recall, in the previous session we were talking about background of the future, right, and we looked what is maybe an ideal system of manufacturing, and what should be the goals of manufacturing. So we are looking for fast, cheap, better and diverse, right. So you should have high speed. You can talk about it should come instantly, it should be economical, it should be of high quality, right, and it should be of high variety. Right? So these are the four goals when we look for manufacturing, and as we discussed in the previous that these goals may be conflicting, right. And then we talked about different numbers, right, like what is the contribution of manufacturing during the Industrial Revolution and how it has actually impacted the global output, right. So then we looked at numbers for India and US, compared those numbers, right. And then we also talked about the importance of manufacturing for employment, right. So we stopped in the previous session somewhere here when we were talking about manufacturing in pre-industrial revolution, correct. So I'll continue my discussion here because we were talking about the iron refining. So one of the things which you might have seen or you might have heard about it is the iron pillar in Delhi, right. So this exists maybe for more than 2000 years, right. I think it was located somewhere else and it now sits somewhere close to Qutub Minar, right. So there are some goodness properties that it has survived for more than 2000 years in an exposed environment. It does rust resistance, and because of the metal, in fact the metal they use is maybe the wrought iron, where the carbon content is very small, right. And it is actually used by using forged welding of pieces of wrought iron, right. So a lot of people have worked on finding what is the metal composition, what kind of technology which allowed it to survive for so long, right. So I know one of my earlier colleagues at IIT Kanpur who was significantly working on mainly this iron pillar, right. So if you just look at this particular pillar, it's a standalone pillar, right. So you don't see many replicas of it, right. So you don't see this maybe in a mass production kind of a setting, correct, right. So you can replicate them, but I don't see it as that easy to replicate, right. And you may not get the exact replica of it. You may always get a variant of it, right. So we are talking about this product as a unique product, and this process through which it is manufactured, we actually call those processes as job shops. So we'll discuss those things. So I'm now integrating some bit of manufacturing and some bit of operations management, right. Now, if I just compare to those four classical goals, right, when we talk about standalone products, they may not be economical at all, because if I just think in terms of the scale part, I have to actually get all the resources only for this particular product or for this particular piece, correct. And even the speed part may not be there, because this is a unique product. There would be a lot of learning as we start making it, right. So you rule out the speed part, you rule out the cost part. You can actually talk about diversity here, because if assume that someone wants maybe a pillar, not just iron, maybe something else, right, or maybe a different height or a different shape. So I can always do customization of this, right. So you can actually talk about maybe diverse or high variety and maybe high quality, because this product in fact has the time is the proof in this case, because if the objective is to actually keep it rust resistant for maybe more than 2000 years, it certainly has served that purpose, right. So, it is not cheap, it is not fast, it is diverse, or it may be diverse, and it is of high quality, right. So, that is something which we normally associate with job shops, correct. But where the question here is, can we improve on these objectives, right. So, is it possible for me to maintain this diversity, to maintain this quality, but improve the speed and improve the cost also, right. So, you actually can produce something which is cheap, fast, better and diverse, right. So, this takes us maybe to about 1500 years later than this iron pillar, even more than that, right. So, I am coming to the medieval times, right, and I am moving from India to the city of Venice, correct. So, there is an arsenal in Venice which is used to build navy ships, correct. And the origin of this arsenal is coming from an Arabic word which is Dar as-Sina, right, which actually means a workshop, right. And if you see this, we are talking about another kind of a manufacturing process which is nothing but the assembly line. In fact, I can say it's a moving assembly line, right. You would see a variant of it as we go into the automotive moving assembly line, mainly for companies like Ford, right. So, you may start building something here, right. It keeps on moving, right. Mast will put weapons, ropes, anchor, right. So, what you actually see is that the 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 goods are moving, right. The the all the other things remains stationary. So, that is why it is called a moving assembly line, right. So, similar thing what you see in the automotive as I mentioned earlier, right. And now we are talking about low volume standardization. What it means is that you are actually improving the variety, correct. When I say improving, it means that when we talk about as I talked about earlier about the Ford assembly line, when I talked about mass production, there was no variety at all. But in this case, there is some variety, correct. And what it is doing is that there would be interchangeable parts, right. So, it means that mast are put at one point, right. So, this particular operation will be they are only expert in this, right. So, someone who is putting the weapons, they will be expert only in this, right. So, we are actually observing what we may call as a learning curve. We'll talk about that, right. So, there would be certainly some cost savings because of replication. So, someone who is actually doing the things again and again, the cost would actually come down, right. But this is still a low volume because the volume of number of ships was not very high, right. So, when I go to a automotive assembly line, I will say that it becomes a high volume standardization, correct. So, this is the first documented assembly line, and this idea of learning curve will actually extend into the modern times also, correct. So, now if I just ask the same question that what is actually happening in terms of cost, in terms of speed, in terms of quality, in terms of diversity, certainly the speed would be higher because people are now experienced, right. So, as I mentioned in the iron pillar example, there would be learning as you start manufacturing something, but in this case that learning has come already, right. So, the speed would be higher as the cost will come down because of this learning. So, there would be a learning curve effect, right. So, cost may also be lower, right. Diversity certainly has come down because now we are talking about low volume, there would be a standard product, right. So, you cannot make all kind of products, right. Quality may be reasonable, right. So, they may not be that could be debatable, but for time being, let us just believe that this has survived more than 2000 years. We are not sure whether we can say the same about the quality in this case, right. So, quality may be reasonable, but certainly the cost and the speed has improved, diversity has come down, right. So, you can actually start looking at the trade-offs already, right. So, all these four things cannot be achieved at the same time. So, as of now, we are not saying that these four are impossible to be achieved together, correct. I think the flow of the course would go in the direction where it is actually possible to start thinking that all these four goals can be achieved at the same time, right. So, yeah, so one thing which comes again here is, so in the Chinese example, when we talk about the blast furnace, we were talking about economies of scale, and now we are talking about the learning curve, right. Yeah, so I'll just show you one ship which is coming out of this arsenal, right. So, interchangeable parts, and it permits variation, right. So, this becomes important. So, when I talk about low volume standardization, I am talking about interchangeable parts, and I think the Americans have expertise complete in this when they go to the modern assembly line, right. Right. So, this is manufacturing in the pre-industrial revolution. I will continue with this, we will give you one more example, and this is from a battle which was fought between the Britishers and the French, right. This was in 1805, and this cannon is called as the 32-pounder cannon. So, in this battle, in terms of the numbers, the Britishers was on the lower side compared to the French, but they eventually the British won the battle because of this particular cannon, and this has an advantage of, because it's a higher rate of fire, and again this concept would be important because the setup time for the next fire was very small in this particular case, right. So, the technology became relevant again, that you actually can reduce the setup time for the next fire, and this concept of setup time we are going to see significantly in this course, that whether it is possible for the technology to reduce the setup time substantially. And then there are some laws of manufacturing which relate the setup time to how much inventory would be there, correct. So, setup time reduction is actually really important in the context of manufacturing. It will impact inventory, it will also impact the speed, right. So, when it reduces inventory, it will improve the cost. When the setup times goes down, the speed also goes up, correct. So, all these, so if you just start building the concepts, we have economies of scale, we have learning curve, we have the setup time, right. So, all these things keep coming together, right. So, I am going to combine all these ideas, all these concepts together, and we start looking into how we can actually improve manufacturing by using these concepts, right. So, yeah, so we move now from the pre-industrial revolution to the industrial revolution, right. So, very interesting book by William Rosen, right. It's the most powerful idea, and I have taken a quotation from there which talks about the industrial revolution, and what he claims is the most important invention of the industrial revolution was the invention itself. Because what we are actually seeing is not an invention of one technology, one product. You actually see maybe a series of inventions, right. So, it actually generates that idea that you actually can invent anything, correct. So, these days in fact we talk about disruptive technologies, and lot of people talk about that disruptive technologies, they may not just come in a standalone form, right. So, I cannot say just artificial intelligence, I cannot just say blockchain, I cannot just say additive manufacturing. What we are actually going to see how these technologies interact, and when they interact, they may actually end up in the exponential form, right. So I think those ideas are also important, right? So when I talk about William Rosen quotation, it talks about the, so if you just look at, so this is a very famous Arkwright's water frame, right? So the Industrial Revolution first mainly came in cotton thread. So when I look at those numbers, right, pre-industrial revolution, as I mentioned, India's contribution was 25%. So we were pioneers in cotton thread, correct? So most of the garments, everything was made in India, right? So the first hit for Indian manufacturing was the invention of this Arkwright's water frame, right? In fact, it is claimed to be the first true production machine which is driven by water, correct? And it may be close to a continuous process. So this is another manufacturing process, right? So we have seen job shop, we have seen assembly line, and it produces nothing but the cotton thread, right? So this may be the first, you can say, this may be the initial ideas of industrial revolution. So, so this extends further, right? Correct. So this may be the fourth manufacturing process, the batch process, right? And this came mainly for the steel, and this actually brings steel. We talked about iron, so I am continuing with the Kipling's poem that iron and steel forms the catalyst of growth, and this may be true even today, right? So whenever we talk about, we may be looking at different types of steel or iron, but I think in terms of the material usage, they still are the dominant ones, right? So this converter, so if you just look at this particular thing, right, what it actually says is, so we are talking about the speed now, right? So steel making process will become faster, and Andrew Carnegie used this converter, and he actually brought some more complementary ideas to produce steel as a batch process. And so economies of scale, all those ideas, they combined together, blast furnaces, right? And by 1899, the Carnegie Steel became actually the largest steel producer in the world, correct? And the cost also substantially reduced, right? So you can actually see the benefits of what scale actually can bring, correct? And maybe matching the right product with the right process. So we are going to talk about that, right? So this also is one of the major leap during the industrial revolution, that you actually can, so steel becomes like maybe the back end of most of the things, right? So we are going to talk about say steam, electricity, maybe computers, right? Now we are talking about digitization. So these may be different general purpose technologies which have impacted different eras of industrial revolution, right? Industry 1.0, 2.0, 3.0, 4.0. But at the same time, as a general purpose technology, steel also has contributed significantly, right? May not be today, but at least in industry 1.0, steel became one of the major movers, right? So, so these ideas keep on rolling. I think as we mentioned, that invention itself was the prime invention during the industrial revolution, and we keep on seeing the different. So we talked about that cotton thread example. So we keep on seeing more inventions, right? So so then we go to a different process. We have seen that in cotton thread, the continuous process, right? So some of you might have watched maybe food factory on National Geographic or Discovery. You would actually see that most of the processes they use are continuous process, correct? So a simple process which produce say only say ice creams, right? So the initial examples of continuous process was the grain milling, right? and a company like Pillsbury comes out of it, right. So there is no variety at all. So what you produce is just the same thing, correct. So you see the examples of chemicals. So you might have heard about the Solvay process to produce alkalis, right. So this is a Solvay process plant. So Solvay brothers, they started the plant in US, right. So these are all continuous process, correct. So the advantage comes because of there is no variety, right. Now if I just again compare those four objectives, because there is no variety, the learning effects may be substantial, right. But only disadvantage of these things, it is capital intensive. So when I talk about a continuous process, it's pretty capital intensive, right. So it actually makes sense to produce in large volumes so that the cost actually divided for the units, right, correct. And that is where we try to have a continuous process for high volume products, right, which are actually needed in high volume, right. And so when we talk about high volume, certainly in that case the variety part goes off, right. But they may be fast. Because of low variety, they may be high volumes, right. So the cost will come down if there are high volumes. No variety, and the quality may also be good because there may be a good control on the process, correct, right. So what we have learned in this case, that we have seen four different processes, right, from the job shop to assembly line to a batch process to a continuous process. And so these forms the four traditional manufacturing processes, and the important part is how we actually map them to different types of products, right. So I think that is what is going to come now. So yeah. So before I go into that mapping, I just want to take a wisdom from what we have learned till now, right. So the one thing which comes out very significantly in the whole discussion, that large is beautiful, right. So we have seen right from Chinese blast furnace example that when you actually scale the things up, the cost goes down. Maybe the other objectives will suffer, but the cost significantly goes down, right. The more is produced, the cost goes down, and we actually call it economies of scale. We are going to look this in technical sense also, but for time being, this is the wisdom, that the more you produce, when the volume goes up, the cost comes down, and we call it the economies of scale or the scale effects, right. Then there is also a learning part which says that the more often a process is repeated, the cost goes down and the quality goes up. So I think this particular thing we have seen in our shipbuilding example, right. When we talk about the interchangeable parts, so it means that the same operation is repeated multiple times, and the learning effect comes in, which may be missing in the iron pillar example, and you would actually see that the cost comes down and the quality goes up, right. And this is actually an example of what we call as learning curve. In fact, if I recall correctly, there was an aerospace engineer, Paul Wright, who tried to estimate the learning curve effect in the aircraft manufacturing, and he estimated that if you double the aircraft production, the cost will actually come down by 20% for each aircraft, right. So that is the kind of scale effects or learning effects we are talking, right. So this has been summarized well in a very famous article written by Professor Bush, as we may think, in 1945. I request everyone actually should read this. it gives the glimpse of technology, right? So, machines with interchangeable parts can now be constructed with great economy of effort. Witness the humble typewriter or movie camera or the automobile, right? The world has arrived at an age of cheap, complex devices of great reliability, right? So, we are talking about quality now, and something is bound to come of it, right? So, this is something which has been told in 1945 when all these effects have already been observed. And one thing which has again come out, that the lower the variety, the higher is the speed of manufacturing, right? So, if I actually can find a way to lower the variety, then, or let us put that if I achieve or if I want low variety, I can actually achieve high speed, right? So, that trade off will be in terms of whether you want high variety. So, when we talk about business, we talk about business strategy. So, some companies leverage variety. It means that their USP is to produce high variety, right? So, they may not bother too much about the speed side. But some companies will look at the cost as a strategy. They may not worry too much about variety. They may look for speed, right? So, if I recall the Ford example, Ford actually tried to forego variety. So, he does not want variety, but he wants high speed, right? So, these what do you call tensions between these four goals will always be there. But again, the question here is whether the modern technology allows us to achieve all these four at the same time, right? So, with this, I'll conclude this session. In the next session, we are going to talk about how the manufacturing processes are optimally mapped to different types of products, right? And our discussion will also move to looking at defining what is mass production, what is mass customization, and mass personalization, right? So, our next session would be on those topics, right? Thank you.